All right, so in this video, I would like to finish the proof of Stirling's formula. So far, what we know is that n factorial is asymptotic to this expression right here. And our goal is to prove that n factorial is asymptotic to this expression. We'll be able to do that as long as that we can prove that this e to the c here is equal to square root of 2 pi. So to accomplish that, we're going to use another formula that I won't prove in this video, but I will prove in another video, which is that the limit as n goes to infinity of this expression so 2n minus 1, 2n over 2n plus 1. So the limit of this expression is equal to pi over 2. So like I said, I will prove this in another video on my channel. But we can use this to prove that e to the c is root 2 pi. To do this, I'm going to look a little bit more closely at this expression right here. And I want to notice that there are, for a fixed n, there's basically 2n terms in this product. And for each of those terms, the numerator is divisible by 2. So another way to write this is 2 to the 2n. And then if I factor out 2 from each of these, I'll have n factorial squared. So this is another way of writing the numerator of this product, again for a finite n. So that's the numerator, and then the denominator is the following. So it is 2n minus 1 times 2n minus 3 times 3 times 1. So this is kind of like a factorial, but it's only odd numbers, and squared, and then times 2n plus 1. Okay, so this that I just wrote is the same as this expression. Great. So now I want to think a little bit more about this. 1 times 3 times 5, 2n minus 1. And if you think about this, what this really is equal to is it's equal to if I had 2n factorial, and then I basically just divided out all the even numbers. So this is the same as if I divided by 2n minus 2, and then I kept doing that until I reached 2. So these expressions are the same. But the denominator of this expression is actually equal to 2, and then times, well, okay, so it's actually 2 to the n, right? So it's equal to 2 to the n because there's n terms, and then times n factorial. Because if I factor out a 2 from 2n, I just have n. If I factor out a 2 here, I have n minus 1, and so on. And then in the numerator, I still have 2n factorial. Great. So I know that this is true. But now I can substitute that in to this other expression. So I now know that this is equal to 2 to the 2n, n factorial squared. So far I'm not going to change anything there. And then I'm dividing by, and now I'll make the substitution that this is 2n factorial squared. Okay, and then I have divided by 2 to the 2n times n factorial squared, and then times 2n plus 1. So all of this is in the denominator, so I can move the 2 to the 2n and the n factorial squared to the top. And so I get that this is 2 to the 4n, n factorial to the 4th power, and then divided by 2n factorial squared times 2n plus 1. Great, but we already know what n factorial is asymptotic to. We know that it's asymptotic to this expression that I wrote up here. And so this also means that 2n factorial is asymptotic to, and then I can just replace all of this by 2n. So 2n to the 2n plus 1/2 e to the negative 2n e to the c. So now I can use that for this expression here. So I know that 2 to the 4n, n factorial to the 4th, divided by 2n factorial squared, 2n plus 1. I know that this is not necessarily equal to, but this is asymptotic to the following: 2 to the 4n, and then I will have n to the n plus 1/2, e to the negative n, e to the c to the 4th power, divided by 2n to the 2n plus 1/2, e to the negative 2n, e to the c squared times 2n plus 1. Great, so now we can simplify this a little bit. And if I simplify here, I can keep the 2 to the 4n the same, divide by 2n plus 1. And then on the top, I'll have n to the power of 4n plus 2, e to the negative 4n, e to the 4c. And then on the bottom, I'll have 2n to the power of 4n plus 1 times e to the negative 4n, e to the 2c. And now what I want to notice is that on the bottom, I have a 2 to the 4n, and I also have a 2 to the 4n on the top. So I can cancel those out. That's going to leave me with a 2 to the 1st power on the bottom. So I have 1/2. On the bottom, I have n to the 4n plus 1, and on the top, I have n to the 4n plus 2. So those cancel to n. These two expressions cancel, and then these two expressions cancel to just leave me with e to the 2c. So I have n e to the 2c divided by 2n plus 1. So what we can conclude from this is that because the expression that we started with over here, because this converges to pi over 2, and because these are asymptotic, this expression also converges to pi over 2. Cool, so we are almost done. The next thing we want to notice is that because 1/2 is just a constant, we know that n e to the 2c over 2n plus 1 converges to pi as n goes to infinity. And then equivalently, that if I multiply this by 2, that this expression converges to 2 pi as n goes to infinity. However, what we also know is that you can take the square root of a limit. So if a sequence converges to a value, then the square root of the sequence converges to the square root of that value as long as all the numbers involved are non-negative. So that means that the square root of 2n divided by 2n plus 1 times the square root of e to the 2c, which is e to the c, the limit of this as n goes to infinity is square root of 2 pi. However, the limit as n goes to infinity of square root of 2n over 2n plus 1, the limit of this as n goes to infinity is 1, because there's a 2n on the top and a 2n on the bottom. So finally, that tells you that the limit as n goes to infinity of e to the c is square root of 2 pi. And because e to the c is just a constant, that tells you that it's equal to 2 pi. And that's it. Thanks so much for watching.